So today we're going to do the review of the units 5 through 8 that are on the midterm. So a lot of stuff to cover, so I'll get going. So we start with unit 5 on classification. And I'll post these notes, so if you don't want to try to keep up and listen, you're welcome just to do that. So the goal of classification is to predict a categorical label Y from feature vector X given training data in the form of X, Y pairs indexed by I going from 1 to N. And first we study binary. Binary case, so we can visualize this if we have a binary Y. We can, and this would be for a two-dimensional X, we would have Y, let's say, equals 1 or Y not equal to 1. We can visualize, maybe we have some samples that look like those green X's, and we have some samples that look like these red circles. And so we'd like to come up with a decision region. Actually, okay, that's fine. Decision region. That tells us which X map to Y equals 1 and which ones map to Y equals minus 1. And when we do binary linear classification, linear classification, we can think of that as a two-step process where first we compute a score, Z, and Z takes the form of an intercept B plus W vector transpose times X. This is a real number. Can be positive or negative. And then the second step is we threshold that score. So we compare Z to a threshold T. So we have two cases. Z is greater or equal to T. Then we say that Y hat, that's the approximation of Y is 1, and Y less than T, we say that Y hat is not equal to 1. And there's different ways of choosing T, but we can choose T equals 0 to maximize classification accuracy. Okay, and when we do this linear classification, we can redraw the picture above. I'm going to put a different data set in there, one that's linearly separable. And now the decision boundary takes the form of a hyperplane. Okay, so that's something that happens in linear classification. And now Next question is training. And the way we propose to train, at least at first, is via the logistic model. So we have the model is as follows. We have that the probability that y equals 1, given the score z, takes the form of 1 over 1 plus e to the minus z. And if you plot this, it has a sigmoidal shape. Crosses 1/2 at 0. And this is also called sigmoid. Okay, so that's the statistical model. And then we use maximum likelihood estimation. So we say that the parameters of the model, which are b and the w vector, these are the ML1s, is the arg max over b and w of the product over I from 1 to n of the probability of yi given zi, or the probability mass function. And then for zi is b plus w transpose xi. So that's how the parameters come into the model. And we went through the derivation of this, and we found we can write this as arg min over b and w of a sum, I going from 1 to n, of the natural log 1 plus e to the zi minus yi zi. And then this holds for yi in set 0 and 1. And then this thing is called the binary cross entropy. Or BCE loss. Okay, so that's how we handle binary linear classification.
Please show T in diagram, threshold in diagram. T.
Let's see, so the location, so the x along this line correspond to z equals 0. So I mean, I guess one way to visualize it would be that if you have a positive threshold, that would create another line over here. So the x such that z is greater than t would be this line where the distance between here and here is t. So
it affects B.
Well, no. So we're saying b and w determine where this line is, and they determine what z is. Second question is, how do you threshold z to get y hat? Separate issue, right?
So T could be nonlinear.
T is a fixed number.
Okay. But it couldn't be nonlinear, something like, let's say, T to the power of Z.
T is just a fixed number. It's the threshold on z. Okay, so that gives us binary linear classification with the logistic model. And then the next thing we can talk about is what happens when we have more than 2 classes. Okay, so in this case, we can still use our linear classifier idea, and now we would compute score zk using bk plus wk transpose x. Again, that's a real number. But now we do this for each class, little k, going from 1 to capital K, which is the number of classes. And then second stage, we say y hat is the arg max over k of zk. So I guess I'll put the numbers 1 and 2 there. Okay, so that would be how we do the linear classification. And then next question, how do we do the training? So for training, there's two possibilities. I'll call it possibility A is 1 versus rest, or sometimes called OVR. And the idea is that for each class, little k, going from 1 to big K, what we do is we train BK and WK using binary logistic regression. So when we do this, we design each of these guys, each of these pairs separately. First, we design the pair for k equals 1, separately for k equals 2, and so on. There is another option called multinomial logistic regression, or MLR. And so for here, we use a different model than the binary case, though it's similar in spirit. Probability y equals k given the score vector z equals the ratio of e to the zk divided by the sum of all L going from 1 to capital K of e to the power ZL. Okay, and here again, ZK is BK plus WK transpose X. And so that's how those parameters BK and WK enter into the model. And then finally, once we have that model, we can do ML estimation, where we say, look for the arg max. Now we have a whole vector of B's, and we have a whole matrix of weights W, and we look at the product of the probabilities that yi equals k given zi. And we have here where zi is the b vector, that's the zi vector is the b vector plus the W matrix times xi. Okay, so that is how we do maximum likelihood estimation here. And We also talked about performance metrics. This is going to be for the binary case. We have accuracy, which is what we usually focus on. This is the probability that y hat, our guess, equals y. But in some applications, that might not be the most important thing. You might instead care about precision, which is the probability that y equals 1, the true y equals 1, given your guess equals 1. You may care about recall, which is the probability that your guess equals 1, given that the true label equals 1. And we talked about some others as well. And one point is that by choosing the threshold t, we can trade off between various metrics like precision versus recall. And sometimes to visualize that, we make a plot. Oops. So we might have there's different ways we can make this plot. We can plot precision versus recall. Another common one is you plot on the horizontal, you plot probability that y hat is 1, given that the truth is not equal to 1. So that would be the false alarm. And then the other axis, you do probability that y hat equals 1, given that y equals 1. So that's the probability of detection. And for different choices of t, you get a certain point on that curve, and so by tracing out over all the possible different t, you get a curve. And now, if you want to measure the performance of a classifier without considering a specific t, you can look at something called area under the curve. And this is called the ROC curve, or the receiver operating characteristic. That's what that curve is. So AUC is a threshold independent metric. So sometimes that's very useful because you don't want to decide on any particular threshold. You just want a classifier that's good for a range of thresholds. Okay. So that covers Unit 5, which focused on classification, but especially logistic-based classification. So then we went on to Unit 6, which was on optimization and gradient descent. So for this, we first started talking about the gradient. So there's different ways we could formulate it, but let's say the W is a vector with D entries. And let's say that our cost, J, operates on W and outputs a real number. Then the gradient of that cost with respect to W is going to be the vector of partial derivatives of J with respect to the different elements in W. Okay. So this is going to have the same shape as W. And this idea we can also do this for matrices, tensors, and scalars. So it's a general idea, this idea of the gradient. But overall, the gradient tells us the slope and direction of maximum increase of the cost of the current W. Okay, so that's the gradient. And then we can use that in an algorithm. Gradient descent, GD, optimization of a smooth cost J. And by smooth, we mean that the gradient exists everywhere, so we don't have to worry about it not existing. So the algorithm goes like this. We start by initializing W at some point we'll call W superscript 0. And we will iterate for index T going from 1, 2, 3, and so on. The following step, W vector at index T plus 1 equals W vector index T minus alpha T, which is a small step size, times the gradient of J at WT. So alpha T is a small positive step size. Okay, so we did some analysis of this. And basically what we found is for sufficiently small alpha T, we proved that the cost at WT plus 1 is less than or equal to the cost at WT for all T. And we did this using this inequality. So we derive that J at WT plus 1 equals J at WT minus alpha T times the norm of the gradient WT squared plus another term, maybe I'll write this as plus alpha t times another term, which is a term which is something on the order of the gradient J WT. And essentially, when we look at those last two terms together, because of the minus sign here, the plus sign here, and the fact that this is on the order of the norm squared, and here we have the norm squared, if we make alpha small enough, then this term will be smaller in magnitude than this term. And so if this is bigger, the negative will overwhelm the positive, and this whole thing will go less than or equal to 0. So this is less than or equal to 0 if alpha t is small enough. So this gives us some confidence that gradient descent will work. And it also motivated another adaptive step size variation of gradient descent called the Armijo Approach, or we'll call it Armijo step size adaptation. The idea is that each iteration t, we perform our gradient descent update. Then we do a few extra things. First, we check if the new cost is less than or equal to the old cost minus some number. I'll put it in red, call it 1/2 alpha t times the gradient of J WT quantity squared. So we check if that happened. If it didn't happen, that means that the step was too aggressive. So we set alpha t as some number smaller than 1. Again, I'll write 1/2, but it could be something that we change. So we somehow decrease alpha t and try the teeth iteration again. So we pretend that it never happened the first time. Okay, but if it did pass, then we actually say, well, maybe our step size was too small. Let's try increasing it. So we can multiply it by some number greater than 1. For example, it could be 2. And we accept the iteration. So the parameter WT plus 1, that parameter vector, we say, great, let's use that. Let's increment t. So we go on to the next iteration. And So these numbers here, these are adjustable. You can change them. Sometimes you can get it to work better with slightly different numbers. Okay, so that was the Armijo rule. And the last thing we talked about, let's talk about convexity. We said that if J, the cost is convex, then all local minimizers are global minimizers. And so we can draw a few pictures here. Let's say I have a situation like this. This would be non-convex. The danger is that if I start gradient descent over here, then I will converge down to this local minimum and I would get stuck there and I wouldn't be able to escape it. On the other hand, we might have something like this. This would be one example of a convex cost. This is a quadratic cost. So if I start here, well, in this case, there's only one local minimum, and it's the global one, so that's great. We get it. But there's other examples of convexity. Like here's a convex cost. This one actually has multiple minimizers that are all global and local minimizers. So any of them down at the bottom are equally good. So these are just some examples. And then some examples of costs that we've seen would be RSS, logistic regression, and the L2 and L1 regularized versions, and also the hinge loss that we'll talk about in just a moment. This is for the SVC. Okay, so that's Unit 6. So moving right along to Unit 7. Unit 7, oops, on the support vector classifier and support vector machine. So let's see, so when we start out, we again come back to the world of binary, linear, classification. And we can draw a picture of a data set that has some red data points over here, some green ones over here, and again, this is like x2, 1, this is our boundary. And one thing that's interesting is that the boundary is perpendicular to our weight vector W. Furthermore, when you look at the zero crossings, we get, we're on the x2 axis, then the zero crossing happens at B over W2, and on the x1 axis it happens at, minus B over W1. So we can see how the weights and the bias or intercept affects the location of the decision boundary. What we can also do is we can also look at the distance of a point to this boundary, and we can measure it and give it a name, gamma I. And so the equation for gamma I we derived was B plus W transpose xi over the norm of W. So this is the signed distance from xi to the boundary. And it's signed because usually distances are positive, but this one could be positive or negative, and it depends on which side of the boundary we're on. So when we're on the side corresponding to yi equals 1, then this distance is positive, and if we're on the side corresponding to the negative or the not equal to 1 labels, then this gamma I is going to be negative. Okay, so that's one important concept. Then we talked about next one was linearly separable. So when we talk about the training data, we can say it's linearly separable or not. Intuitively, if we can pass a line through the training data that splits it perfectly into, on one side of the line we have all the samples with label y equals 1, on the other side of the line we have all the samples with label y not equals 1. If that can be done, then it's linearly separable. But in this unit, we came up with a more mathematical definition. So linearly separable data means that there exists some pair B W vector such that yi times the quantity B plus W transpose xi is greater or equal to 1 for all I. And equivalently, you can say that the signed feel like there's I have a mistake here. I think we might need like okay. So I was going to write this, that this distance is greater or equal to 1 over norm of W, but I feel like
there's a y in there.
Yeah. There should be a y here, right? Yeah. Okay. And this last quantity we define as the gamma. Okay, so if this happens for all I, that's another way of writing linearly separable. And this quantity here is known as the margin. And we can draw a picture the data again. Here's the hyperplane. Here's the data. Let's see. Actually want to move this. Oops. It's not helping. I want to move this over a little bit. Okay. Okay, so now we can draw a little street. And the width of that street in either direction is gamma, which is that margin. So we can fit a street in there, and we can push the street wide enough so that this sign-corrected sign distance is greater or equal to gamma, and furthermore, we can connect gamma to the 1 over the norm of the weight vector. Okay, so this idea led us to propose the hard margin classifier, which said, let's try to make the width of the street as large as possible by selecting B and W appropriately. And in terms of the math, that means let's minimize the squared norm of W, which is like maximizing that gamma, the margin. But of course, we have to do this while keeping the data linearly separable, so that's such that yi times B plus W transpose xi is greater or equal to 1 for all I. So we're putting together linearly separable margin, and the idea that we want to make this as wide as possible so that we have a robust classifier. And so that gives us this approach. The trouble with this approach is that it's only feasible when the data is linearly separable. So in practice, we have a lot of non-linearly separable data sets, and we can't apply this idea to it because there is no classifier for which these things hold. So we came up with a generalization called the soft margin or support vector classifier, the SVC. So this one, for this one, we converted that inequality to a cost term. So we want to minimize some constant, which we can choose, C, times the sum for I equals 1 to n of the max of the number 0 to the number 1 minus yi zi plus 1/2 norm of W squared. And this zi is where the weights come in. So zi is B plus W transpose xi. This term here is called hinge loss. And in terms of this number C, as C increases, the margin gamma decreases, and we have a bias variance trade-off. When the margin is small, relatively few of these samples determine the margin. Those are called the support vectors. When gamma increases, then more and more of these are used to determine the boundary, and the bias goes up, but the variance goes down. Okay, so coming back to the SVC, the solution, which we'll call B star, W star, depends only on the support vectors, some subset of the training vectors. And the support vectors are the samples xi such that yi times b star plus w star transpose xi less than or equal to 1. So these are the ones that are on the boundary of linear separability or violating linear separability. Okay, so that's the SVC. So it's a pretty good approach. We see that it often performs a little bit better than logistic regression, although not too much better. And that leads us to the next approach, which is the SVM. So the SVM is an SVC with a usually nonlinear transformation and takes your raw feature vector x to some new, typically higher dimensional feature vector phi of x. So phi is the transformation. But the SVM avoids directly computing or even defining phi. Instead, it computes the kernel kappa, and so if we have, let's say, two vectors, xi and xj, this kernel, we can relate it to the transformation phi. It's like phi transpose xi times phi xj. So it uses this kernel, and it relies on the dual form of the SVC optimization problem. The most popular kernel is the radial basis function kernel, which takes the form kappa as a function of xi and xj is the exponential of alpha times the norm of the difference of xi and xj. And then this alpha is a tunable positive number. All right, so that covers Unit 7. Let me try to hurry through Unit 8. I have a little bit less to say, so I don't think it should take too long. Unit 8 is on neural nets. So the main idea is, can we learn a feature transformation V from the training data? That's the essential question. And then the answer here is yes. We will use a specific form for phi. So we're going to look at the lth element of the phi vector. And this is going to be some nonlinear, some scalar nonlinearity gh times an affine linear function of x. And of course, this is going to happen for several L. One, call it to DH. DH is the number of hidden nodes. So once we do this transformation, and then do linear classification, or we could even do this with regression. So that's the idea. If we draw this as a block diagram, get something like this. The x vector comes in, multiply it by matrix WH. We add on a vector BH, biases or intercepts. Then we put these through these scalar nonlinearities, GH. And then we go through a linear prediction layer. Could be, you can think of it as a classifier or a regressor, but we take, so this is U of H. It's coming out there. We take that, do an inner product with WO, add the output bias BO, and this gives us the output score. And we said that we can visualize this, can make a data set, something like this, which is a non-linearly separable data set. But what we can do now is we could do something like this. We could have, so these biases and weights, each one, for each one of those L, they define one of these boundaries. So if we have 4 of these guys, that would correspond to 4 of these. And then we take the numbers that come out of that first stage. Okay, we take out those numbers, we put them through some nonlinearities, and we have a second linear stage. And that will eventually allow us to do like an intersection of half spaces where we can classify those points being from the red class and the other stuff outside being from the non-red class. So, yeah, so we would finally do here, y hat is sine of the output. Okay, so that's the architecture now for the training. So let's put our parameters all together in an object theta. So that would include the hidden weights, the hidden biases, the output weights, the output bias. We train that to minimize some cost script j of theta, which is defined as the sum over our training samples of a per sample cost non-script j, which is a function of theta and of the ith x and y. And we do this minimization via gradient descent, which again we do theta t plus 1 equals theta times t minus alpha t times the gradient of our script j evaluated at theta t. Or we also discussed splitting this into mini batches. Okay, and then the last thing is how do we compute these complicated gradients? We use something called BackPropagation. So to help visualize how we do the computations, we draw the computation graph. So the graph shows how the different variables are connected to each other. Okay, so we have sample vectors xi coming into our system using the hidden weight matrix, hidden bias vector, and those samples coming in, we can compute the hidden scores. Using hidden scores, actually, sorry, this year I changed the notation. So instead of calling these U, we've been calling them A. So let me make that change. Sorry about that. Okay. I think that's all I have to change. Okay. So over here, we have our activations. These are our hidden activations, AHI. And then with the activations and our output weights and bias, we can compute our output scores. And from those, we can compute our cost J. Okay, so finally, we train using backpropagation consists of a forward pass and a backwards pass. In the forward pass, we compute first ZHI, then activations AHI, then output scores ZOI, and finally the cost J. In the backward pass, we use all those computations and we go in the reverse order. So we compute first DJ DZOI, and then we compute DJ DAHI, and then we compute DJ DZHI. And we can also then compute DJ DBO, DJ DWO, DJ DBH, and DJ DWH. And so those are the quantities that we need in our gradient descent step. And then one last thing is we use the multivariate chain rule. So for example, if I want to compute something like DJ DBO, I can do this because there's many paths between J and BO. Because we have many I, we have to have a sum over I. And then we have DJ DZOI times DZOI DBO. So this is the multivariable chain rule. Okay. So that's everything. I apologize for going a few minutes over today. If you have any questions on any material, please reach out to myself or the TA or post something to one of the discussion boards. But otherwise, we'll see you guys Friday morning here at 8 o'clock for the exam. And all right, see you guys then.